be able to introduce Gil Holder today. And so Gil and I have known each other quite a long time because we actually overlapped in graduate school. He was finishing when I was starting. So it's been quite some time. Gil is one of these theorists that just has lots and lots of imaginations of finding just lots of really cool things that you can do with the CMB. And so that goes from things that you can do from the CMB alone to things that you can do with cross correlations. He's worked on CMB lensing. He's worked with massive clusters with the C. He's worked on some millimeter sources. He's worked on stellar flares with millimeter detectors. So he just has boundless creativity on things that you can do with millimeter wave instruments, in addition to other things. So he has a broad range of things, gravitational waves. So it's just a large things, but as I said, lots of creativity on things that have to do with the CMB, and I think that's what you're going to be telling us about today. And of course, I'm an idiot, and even though this was right there, I already forgot to announce that these are the winners for the TAP Prize for Travel Awards, and I believe some of the people here are in the room. So if we can congratulate our winnees. And with that being said, go ahead and take it away. Oh, and I have to launch it. Jeez, I am falling on the job here. Let's do this.
All right, what has happened?
There you go.
There we go. All right, well, thank you for reminding me how old I am. That's great. All right, so I'm going to talk about mainly some CMB and also just some stuff about galaxies, because I know there's lots of galaxy people here. Before I get going, though, as Eduardo mentioned, I am interested in stellar flares. So if anyone here knows anything about stellar flares, I'm interested in them, but I don't know anything about them. So I really need your help. So please come see me. Or if you know about thermal emission from asteroids. If anyone knows anything about thermal emission from asteroids, I need help. So just remember that. Please find me if you know anything about those things. All right, so what am I going to talk about? So I'm going to talk about using large-scale structure as a tool for astrophysics. So it's really interesting to measure large-scale structure just for its own merits and learning all sorts of things. But I'm just going to talk about some other things you can do that could inform other bits of astrophysics, just kind of laying it out there. So there's 3 examples. So one's project that one of my grad students is working on, so correlating high energy neutrino maps with galaxies. So there's this problem of the ice cube neutrinos and not quite sure what they are. Maybe large scale structure can tell us what high energy neutrinos are. I'm going to talk about gravitational lensing of galaxy clustering. So not by galaxies, of galaxy clustering. And then I'll talk about the kinetic Synyav-Zeldovich effect as ways to look at various re-ionizations, plural. All right. So there is large-scale structure in the universe. What do I mean by that? Well, I mean, here's this just kind of dizzying graphic made by Reese Menard and Sharkman. I don't know who that is, but these are galaxies of various forms. So the main point of this is I just wanted a picture of a bunch of galaxies that are clumpy. And here you see a bunch of galaxies, and you see that they are all lumped up. So the main takeaway from this slide is that we have measured a lot of galaxies. Lots of galaxies have been measured, and they're clustering. So, you just see all of this fine scale structure. That's real galaxy clustering in the universe. It's very well measured. Lots of good reasons to measure it better. So I'm very glad that there are people here measuring it better. You can always measure it better. But can we use this for other stuff? So that's my question for today. So I'm going to give you a case study of a few different things we can try. So one, let's put this to work. So could we use this amazing grid to see if we can figure out where neutrinos are coming from? So there's this problem of, so ice cube is, so I work on the South Pole telescope. That's what most of my work is. And it's at the South Pole, as is ice cube. But ice cube measures these high energy neutrinos coming through the ice. And presumably these things are produced by some cosmic ray collisions extragalactic for the most part. So cosmic rays at very high energy hit stuff. So either off of photons or off of other particles. They produce the pions. The pions decay. One of those decay products will be neutrinos. Those neutrinos go across the universe until they go through the ice. And then, or they hit something in the atmosphere and produce muons. And those produce radiation in ice cube. Now, this is not a very technical term here, right? Stuff. So what does that mean? Well, so we don't actually know where these sources are. So if you just kind of try to do a cross match of nearby blazars or star-forming galaxies or GRBs, there's no any one class that comes out as being enough to explain where they're all coming from. However, one thing that we know is that if these things are coming from galaxies, they should be tracing large-scale structure. Galaxies trace dark matter. Whatever these things are coming from almost certainly trace dark matter. So it must be the case that a map of where these neutrinos are coming from must be correlated with the large scale structure that is the backbone of where these things are. So one thing we could do is we could just see if we can get a match where we can just try different tracers of large scale structure and see what we can see. So here are the measurements of, so this is the data set we use. This is the 9.5 year point source data. So the number of events per bin is, so this is the black line. Now, this is almost all background. So they're modeling for the background as some combination of purple and a little bit of Monte Carlo correction. And then here's the astrophysical signature. So you see when you get out here at, so this is the muon energy, 10 to the 6 GeV. Well, so first of all, there's not really much out there. So you go down a little bit and you see that once you get to very, very high energy, it's mainly dominated by the astrophysical ones. And this is why they say we've detected the astrophysical neutrinos. We definitely know there's some neutrinos coming through out here, some that are way over the background. But then you see most of the events are coming from down here where it's much noisier. And then the question is, so here you see number of events per bin, 10, 1, 10, 100. If you want to start doing statistical studies, you're going to have to dig into this part where it's a little noisy. So that's what we'll do. So noise is not scary because large scale structure is a really good template. So the angular resolution is not great. I think maxes out at about 0.5 degree. So each neutrino is kind of very fuzzy. So we're already stuck on large scales here. All right, so are any of these large scale structure surveys correlated with the neutrino map? If they are, that tells us that the neutrinos are coming from whatever large scale structure is correlated with these galaxy maps. So basically, you go out, you just say, what maps do we have that cover most of the sky? And especially the northern hemisphere. So it's this ironic thing that IceCube is at the South Pole, but it's best at measuring things from the northern hemisphere because you can use the Earth to block out stuff that's coming down from the atmosphere and get only the things that are coming through the Earth. So you want northern hemisphere things, or all sky. So there are these quasars catalogs that is WISE plus Gaia. So that's Quia, and there's a couple different redshift spins for that. There's an unwise sample from Alex Kroluski, and so that's got 3 different redshift bins, sort of lower, mid, and high. And then there are the DESI photometric sample, where there are a bunch of different samples there as well. So, here are the different samples we tried just to see what's going on. So here are the DESI bins. These are unwise. And then you have the different Quia samples here. And then the question is, are any of these correlated with the neutrinos? And it's completely just a fishing expedition, like, hey, let's see what we can see. And you never know. So at the very least, you could put limits on whether any of these neutrinos are coming from any interesting fraction of this large scale structure. So we just do a cross correlation with all these things. So you see that these things, they strongly overlap in their various redshift sampling. And then so what you can do is you can basically make combined maps of these things based on their noise, do some signal noise weighting. And so that's the red points. And so here's the cross power spectrum, the cross power spectrum between neutrinos and galaxies for the parts of the sample at less than redshift of 0.5. And what you see is there's definitely nothing obvious there. So we would say, well, okay, well, I guess they're not coming, most of them are not coming from that redshift range. Now we do the same thing with redshift around 1, and actually, you actually see it's still pretty ratty, but maybe. Then you go to higher redshift, and again, it kind of disappears. So what can we do with that? Well, so maybe there was that hint at mid-Z, and so this is sort of, so what I did now is I just said, let's take this line and just take the average CL in this range. So just average for each one of these bins for all the different samples. And what you see is that the mean cluster, the cross power between galaxies and neutrinos in all of these different surveys, you see that there's this odd peak that's individually basically not very convincing, but then you look at the whole thing and you say, boy, that sure looks like ice cube neutrinos are coming from redshift around 1. Now, what's a little tricky about this is, remember I showed you that these are all sky maps with overlapping redshift distributions. So while it's true that it looks like there's a lot of cross correlation, remember that the sample variance in the galaxies is very strongly correlated. So what that means is that these are almost the same maps of large scale structure, just with different bias factors. So what you have to do is you have to include all those cross correlations properly. And by the time you combine all those correlations, what you find is that these things that individually look like you're getting somewhere work out to be just a little over 2 sigma, like 2.5 sigma. So anyway, but so this is an example of what you can do with large scale structure, is you can just use it to, it's effectively like clustering redshifts for ice cube. So now you can go forward and you can say, does this make any sense? So does it make sense that we should see this much clustering given this much noise? And so you can go through and you can model and you can say, if all of these things were coming from something like a redshift of 1, using this red line, what would you expect to see in this measurement? And if you divide it into different bins in the neutrino energy, you'd expect something like this, given what is in that model for the ice cube neutrinos. And what it means is that this is only possible if the amplitude, if the fraction of astrophysical neutrinos in here is substantially higher, or if they're strongly biased. So anyway, so this is just kind of it's a fishing expedition where we kind of got some nibbles. So I wouldn't say we've caught the big one here, but it's interesting. So I think a takeaway you could get from this talk is that it's not crazy that the ice cube neutrinos are coming from redshift 1. It's not, I wouldn't say it's definitive, but it could just be a statistical fluke, right? You try everything and there's a huge trials factor that's impossible to get out of there. So that's one example of what you can do. Now, what else could you do? So I want to put large scale structure to work by using the galaxy clustering as a lensing source. So what do I mean by that? Well, so in general, we've measured galaxy clustering. So galaxy clustering, well, let's put it this way. Here is a nice DES image, possibly made by someone that you know. So this is a DES image. So there's a couple stars in here. But what do you see? You see that you look at any galaxy, and these galaxies have nearby structure. But in general, that nearby structure has a few properties. It's statistically stationary. And what do I mean by statistically stationary? I mean that this part of the image looks a heck of a lot like this part of the image. That's what statistically stationary means. That there's no one spot in that map that looks funny. Obviously there's some spots that have some bright spots and cold spots, but in general, you wouldn't say that looks funny. The other thing is that it's isotropic. It's statistically isotropic, that the fluctuations, if I run along the bottom and I look at the fluctuations as I move across, look similar to the fluctuations in the vertical direction. There's not some vast difference between the vertical direction and the horizontal direction. So now I'm going to just put a lens down in here. And it's a hopelessly unrealistic lens, so don't worry. But I think you can tell where it went. So how can you tell where it went? The mean isn't changed, but there's a couple different properties. So one is you see that everything has gotten bigger. including the galaxies. So everything's gotten bigger. But notice that there's this, so for one, the number density is different. And so that's basically, so that's something you can look for. You can look for magnification bias. But also the characteristic separation between any two objects is very different in here than it is out here. So that's saying that the something about the 2-point correlation function is now stretched out to much larger scales. So what else do you notice? Well, you notice down here, you can see these galaxies have different shapes. So you could measure the shapes of these things, and you would then be doing a cosmic shear experiment if you actually looked at the shapes. But not only are the shapes different, but just like the characteristic separation has changed here, the characteristic separation here now has broken isotropy, right? That the fluctuations going along this tangential direction are different from the ones in the radial direction. So even if you just treat these things as positions, the distance between galaxies has a characteristic distance along the tangential direction that's different from the radial direction. So we've broken statistical isotropy, that this part of the image is different from everywhere else. And then even with where it's different, in some spots, it's not isotropic anymore. So if you were to just run your 2-point correlation function estimator, you would say, oh, these galaxies all look really, really far apart. There must be some extra convergence here. So by eye, you've just run an estimator to say, where's the mass? Just like you'd say, oh, well, here all the galaxies are further apart in the tangential direction than in the radial direction. There must be something going on here where there's a big lump of mass down there. You've run a shear estimator in your mind. And that's different than what you do if you're actually measuring each galaxy on its own, right? You could also say this galaxy is much bigger than normal, therefore this area is magnified. But instead, we're using the characteristic spacing between objects as a ruler. And we're going to look at how that ruler is stretching or contracting, or how it's different in different directions as a way to estimate what the mass distribution is. So this is exactly, so you can now probably figure out where I got to this. I got to this from CMB lensing, as Eduardo said, I've worked a lot on, with the same exact graphic. This is this Planck sky, and there's a lens right here, not quite as big as the last one, but there's still a lens right here, and you see the hot spots in the CMB are bigger and smaller. And then you see here, I've broken the isotropy. So, so in the language of how we construct this in CMB lensing, we'd say you have some lens field, and that's actually the unlensed field at some different location, right? That's what I just did. I took the unlensed field and I just moved it to a different location. So similarly, the lensed field is the unlensed one at some undeflected spot. Now, if you just do a Taylor expansion on that, you see it's whatever it was unlensed plus grad T times the deflection. So in one way of looking at this, you see that there's this deflection, which is proportional to the gradient. So if I multiply this by the gradient, then I'll get a big square right here, grad T squared. I take a Gaussian field, square it, and it becomes, I just get some variance, but I end up with something that's just proportional to the deflection. If instead I think about this in harmonic space, I Fourier transform this whole thing. So if I Fourier transform it, this lensed field becomes whatever it was before. Then I have a gradient dotted with something. So this is a multiplication. That becomes a convolution in Fourier space. But in general, it's this idea of a quadratic estimator, that I can construct an estimate for the deflection that's just based on how something about the square of the map is behaving. So that's what you were doing when you're seeing that there's a lens here. You're saying the 2-point correlation function has some particular scale in the middle that's different than the scale out here, but that's a 2-point correlation function. It's not the mean, it's how the variance is depending. So, so this is how we make CMB lensing maps. So, so here's a CMB lensing map, and I'm going to tell you that I believe that this is the largest wide-angle lensing map ever made. Sorry, the highest signal to noise lensing map ever made. I think it's actually deeper than the HSC map in terms of signal noise per pixel on degree scales. That's not what we're talking about. So back to galaxies. So here's that unwise galaxy catalog from Alex Gralewski. Again, we do the same thing. This is just number counts now. So now I've taken each galaxy and just made it either ones or zeros. This is the number of galaxies per pixel. And again, we see you can lens that thing, and what do you get? You get some characteristic change in the galaxy number counts, depending on whether there's a lens there or not. And so we run that same quadratic estimator, and we could use that as a way to reconstruct where all the mass is that's doing the lensing. But if we do this with galaxies, we can now do it for galaxies at redshift 2, galaxies at redshift 1.5, galaxies at redshift 1. We can build up a lensing mass at every spot along the line of sight. So looking forward to LSST, so what do we know? Well, we know that we will have these galaxy maps at a bunch of different redshifts. So, so Brandon Bunchers, a grad student at Illinois, he just went into Cosmo DC 2, and got and just looked at what the angular power spectrum was and compared it with the shot noise. So if you cut it a magnitude of 23 at a redshift of around 0.85, you get some angular power spectrum that looks like this, where the shot noise is here. And what that says is that your map is shot noise limited somewhere around L of maybe 3,000 or 4,000. So that's kind of like where a CMB map is in terms of where it becomes noisy. You do it with a deeper map, something that's down to 25. You look at maybe 1.1, some different shell, delta Z of 0.1. And you see your shot noise limited down almost to arc minute scales. So what this means, so your map is basically, as long as you're at lower L, you have a good map. So on large scales, you have excellent maps of galaxy clustering. So you have these high signal noise maps. You can use each one of these as lensing screens. So I'm going to assume they're Gaussian for this calculation, so that'll water things down a little bit. But we can use this and do exactly what we did before, which is do lensing reconstructions where we find all the spots where these 2-point functions are wrong using an optimal quadratic estimator instead of just using your eye. So it's possible. So I'm telling you that it's possible, but what I was, so then the question is it useful? Now, so it turns out this is incredibly noisy. What do I mean by incredibly noisy? Well, what I mean is that here is the signal power spectrum, and there's the noise up here. And notice this is 10 to the minus 8, that's 10 to the minus 5. We're orders of magnitude in noise above. So for the CMB lensing maps we were making, those CMB lensing maps had a signal noise where the noise was below the signal, which is to say we were making good maps. So here we're making terrible maps. And if you say, if I have all these redshift bins, so remember we have all the redshifts between 0 and as high as we can go. Even then, you add all this together and you'd be lucky to get up to a signal noise of 1, just in terms of trying to detect this effect. So that's not great. However, what you can do instead is you can do a cross correlation with some other estimate. And why would you do this? Well, so let's say that you have a cosmic shear sample where you have some RMS of maybe 30%, and you say, how much signal noise can I get in cross correlation? Well, in cross correlation with, say, the LSST measurements of the shear, you can see that in cross correlation, we can actually get up to almost a signal noise of 80. And so what could you use this for? Well, you could use this as a cross check on your shear measurements. So maybe it's not quite enough to get to percent level shear calibrations, but it's definitely a nice cross check. So that's one thing you can do. However, you don't actually only have, and so the thing about the shear measurements that's nice is that you can take your redshift 1.5 screen, do the mass reconstruction of all the mass along the line of sight to redshift 1.5, and then you can compare that directly with the shear measurements in that same screen. And that is those things are measuring exactly the same thing. There's no wiggle room in there. You have two things measuring exactly the same thing. You can then do a direct comparison. However, you don't only have shear measurements, you also have other measurements of large scale structure. So for instance, you have the galaxy density, and galaxy density is a nearly infinite signal noise map. It is a very high signal noise map, especially on large scales. And you see that you can actually get signal noise of hundreds this way. And so what's being plotted here is for different shells for how good, say, your photo Z bins are. And what you find is that you always do better by going to smaller shells. I'm not quite sure why this one's down there, but you always do better by having slightly thinner shells. And you think that's weird because your shot noise goes up in each shell, but your shot noise goes up in each shell, but your clustering amplitude goes up. So you actually just want the finest photo Z errors you can get. But anyway, now this is in general just a generic, this is, I think, you can think of this as a 3-point estimate because you're doing this background screen. You're doing a quadratic estimate where you're squaring this background screen, and then you're comparing that with some tracer of the foreground matter. And so that tracer of the foreground matter could either be the cosmic shear measured in that same screen out here. That's a tracer of the large scale structure in between. Or you could cross correlate it with the galaxies. But in general, this is something we can do going forward with any set of cosmological tracers that you can do cross spectra. It's basically a squeeze by spectrum. You're doing any pair of tracers that are close to each other at high redshift should be correlated with lower redshift structure in a way that's directly proportional to the lensing. So, it's more information about the lensing in the universe in the foreground, and it's also a cross check on all of your large scale structure inferences. All right. So that's another thing you can do with galaxies. Now, the last thing we're going to talk about, let's see, where's my time? Oh, good. We started at 3:30, right? Okay, lots of time. The last thing we can do is we can say, wherever there are galaxies, there's matter. So the galaxies are tracing the matter. Where there's matter, there should be electrons. So every spot where I see a galaxy, there should be some excess of electrons there. That seems non-controversial, right? That where there's dark matter, there's baryons. Where there's baryons, there should be some electrons, unless it's completely neutral. Now, what happens to those electrons? Well, one thing that happens to electrons is a thing called the kinetic Sunyaev-Zel'dovich effect. So what do I mean by that? Well, so let's say you have a cloud of electrons and it's sloshing towards you. So there you see you have your free electrons. Oh, that got cut off. It's sloshing towards you. You get a general upscattering of photons. So wherever you have electrons coming towards you, the CMB should be slightly brighter. So just Thompson scattering from a moving cloud leads to a small gain in the direction of the motion. So if you're over here, you see some cloud of electrons, the scattered light is a little bit hotter than the light that came in. So that's KSZ. So here is this sort of really nice cartoon that was I first saw from Matt Matavasharil. So how does it work? Well, so imagine that you have this cosmic velocity line of sight mode. So everything over here is moving away from you. Everything over here is moving towards you. Now, here are where all your galaxies are. And remember, where you have extra galaxies, you have additional electrons. So wherever you have additional electrons, you should see, because all those electrons are moving away from you, you should see some general small scale structure that is in general cool, because all that stuff's moving away from you. Over here, everything's moving towards you. So wherever there are excess electrons, you should see some excess small scale structure that's all slightly hot. In between, you see almost nothing, because while there's still lots of electrons here, they're not moving. So what this tells you is that you can, there's multiple things going on. One is that there's a correlation between the small scale structure in the CMB and your galaxies. So if I do a cross correlation of these galaxies with this small scale structure, I will get something that's proportional to the line of sight velocity. So some people have used this as a way to reconstruct very large scale velocities. So that's one thing to keep in mind. The other thing that you can notice is that you have lots of small scale structure over here. You have lots of small scale structure over here. In between, you actually don't have very much small scale structure at all. So this the fact that it's modulated by the velocity means you have, again, you're breaking the statistical isotropy. Different parts of your map will have different amounts of small scale structure. So this is very similar to what we've been talking about in other aspects. This breaking of statistical isotropy will show up there. So you can use this as a way, in principle, you can say, well, if I know what this is and I measure this, I can measure some combination of that line of sight velocity and how many electrons we have. The other thing we could do is if we already have all these galaxy positions, we may have a pretty good estimate already of what these large scale velocities are. And so if we already know what the large scale velocities are, and we know roughly, and we know where all the galaxies are, and this is a way to see what the electrons are doing. So this has been detected. So as I said, the amplitude is going to depend on the relationship between galaxies and electrons, and something to do with these velocities. So this particular signature has been detected by all the major experiments by doing exactly this thing, where you say, I know where the galaxies are. I'm gonna guess what the velocities are using what I know about where the galaxies are along the line of sight, and I'm gonna use that to make a template for what the small scale structure should look like, and then I'm gonna cross correlate them. So that's another way of expressing the pairwise KSZ and all that stuff that people talk about. But the basic idea is that the galaxies are telling you where the small scale structure is, the velocity tells you the sign, the overall amplitude depends on the electrons. All right, so as I said, you can use it to reconstruct the velocities, but if you kind of know the velocities, you can use it to probe the electrons. So why would you want to probe the electrons? It's like, don't we already know where all the electrons are? Well, to some extent, we know where all the electrons are, but we look at the history of the universe, the Big Bang, then there were the Dark Ages, then hydrogen reionization happened. We don't exactly know where all the electrons were during reionization, right? There's lots of people trying to figure out exactly where we went from being neutral to being ionized in hydrogen. However, when people talk about reionization, they're usually talking about hydrogen reionization and the first ionization of helium, because that's what you can do with hot stars. But to get that last electron out of the helium, you need a harder radiation field. And so where are you going to get a harder radiation field? Well, typically you might expect that from quasars. So helium reionization doesn't really complete until we have enough quasars around. And so we think that happens somewhere around a redshift, greater than 3, less than 4.5. So there's lots of circumstantial evidence for when helium reionization happens. But what's interesting about the helium reionization, from the perspective of what we can, at least for this talk, is that redshift 3 and 4, we can actually think about knowing something about where the structure is in the universe. Redshift 8 or 9, sure, we can use JWST to look at these little tiny pieces, and we might know where a couple of the galaxies are, but we don't really know where most of the galaxies are. Certainly not over degree scales, many degrees. But by having sources at redshift of 3 or 4, we can actually use that to figure out the mapping between galaxies and electrons. So remember that in order to get this signal, we need to know how many electrons go along with each galaxy. When helium reionization happened, every electron gained some new galaxies. Every galaxy gained some new electrons, right? So we went from having, one of the electrons was happily tied to its helium. The quasars turn on, that electron is now just in the galaxy. So every galaxy gained 1 electron per helium atom at that point, which, so that's something we could look for. What we should see is that if we do this comparison between the galaxies and where the small scale structure is, if we do that at things before helium reionization happened versus after helium reionization, we should see that every galaxy is a little bit more electron rich. We should see a boost in the signal at lower redshift after helium reionization is completed. So how realistic is this? Well, so you run a forecast and you say, how well can we do with this? So sort of with S4 sensitivity and using Rubin, what you find is that we should be able to see that there's some hint that there are more electrons at redshift 2 than there are at redshift of 3.5. But I wouldn't say it's going to be conclusive. So there'll definitely be an excess. You'll see that this is the electrons per hydrogen atom. Your electrons per hydrogen will, so here it's above 1 because you've already ripped 1 electron out of each helium. Helium reionization happens. You now have added a new electron for every hydrogen atom that you have. So you get this boost. And then what these models are 3 different models that are out in the literature for how helium reionization may have occurred. So you go forward, you look at more futuristic large-scale structure surveys or better CMB experiments, and you see that we could conclusively say exactly how helium reionization happened. So that's in the future. We're looking forward. That's something you can do. And so again, what we're using there is we're using the large-scale structure to tell us something about astrophysics. Now, on a related topic, but it's not quite using the galaxies, is to come back to this diagram. Instead of using the galaxy positions, imagine what would happen if we tried to go to reionization, hydrogen reionization, the first reionization. So there you have all these bubbles. So when reionization first started, you turn on a source, it blows a bubble around it. You now have a shell of ionized electrons, of ionized hydrogen full of electrons around every source. And those things are going to be sloshing towards you or away from you. And now your CMB fluctuations, instead of being these dots from the galaxies, will be these bubble-sized fluctuations, but there'll be a lot of them. Now, everything we've done to this point, we've said, oh, well, we'll just do this cross-correlation with the galaxies and use large-scale structure for our benefit. The problem here is that, at least for the foreseeable future, we're not going to have galaxy reionization maps at high fidelity at redshift of 7 or 8 for a while. Even on the time scale, those forecasts I was doing, I think no one's really designed an experiment that's going to give us really good maps. However, you can go back to this cartoon and notice that the power spectrum has these big fluctuations in it. So you have lots of power, no power, lots of power. And by not having this template, you can't use the sign to be informative, but you can use the fact that there's extra power in some spots and there's dead spots in the field that correspond to these voids, or sorry, these nulls. So right here, there's no small scale structure because you're at a null of the velocity field. Now, reionization happened reasonably quickly, which means there aren't very many line of sight modes. So we don't have the template, but the fluctuations are large. It's going from neutral to ionized. It goes from 0 to 1. Whereas remember what we were doing before, we were talking about neutral fractions going from just below 10% to just over 15%. Now we're talking about neutral fractions going from 0 to 1. So they're very large fluctuations. There's almost no line of sight averaging because it happens relatively quickly along the line of sight. So the signal can be quite large. However, the only thing you can look for is spatial variation in is in the power. So so we went looking for this. So there's, just like there was an estimator for CMB lensing where you just basically take the gradient of the map and you multiply by the map. The estimator for this effect is you just want to take a map, you want to filter it on the characteristic scale of whatever you're looking for. So if there are galaxies, they'd be this scale, or KSC from reionization, you might filter on slightly larger scales. Depends on exactly what scale you're trying to optimize. You're going to take your map, you filter out so that you're focused on the scales you care about. You want to get rid of the CMB fluctuations. You want to get rid of small scale noise, get rid of foregrounds. So you just very carefully just filter out the long wavelength fluctuations. Then you just ruthlessly square your map, which sounds crazy, but you just square it. That's what the optimal estimator is. You do the math and you say, it tells me to just square the map. So, okay, you square the map. So you filter it, you square it. And then what you'll find is that the square of the map will generally be large in regions like this. And it'll take on a smaller value in regions like this and a larger value in regions like this. So it'll be a mean, right? You've squared something. So its square is always bigger than 0. So even here, you're going to get zero, you're going to get something bigger than zero just from noise. But then the excess compared to noise, you'll get a big signal here, you'll get a big signal here. You now have a map of where all the excess power is. And in general, you have large scale splotchiness in the amount of small scale power. I'm going to say that again because it's confusing. We have large scale fluctuations in the amount of small scale clustering. So we're going to take the power spectrum of this squared map and see if we see these big fluctuations. And those fluctuations will be happening on scales that correspond to the velocity field. So we should see big fluctuations on the scale of that the velocity field varies. That's coming from how the small scale structure goes. And you say, what scales are these? Well, these are scales of several degrees. So on scales of several degrees, we should see this fluctuation, and the re-ionization piece should be quite large. So we took our telescope. So using the South Pole telescope, here's the South Pole telescope before the ground shield was up. So it's been running for a while. So we're now on the, I don't know what happened to my SPT3G. So here's SPT3G. We have 100, 150, 220 gigahertz. It's polarized. And our map depths are something like well below 5 micro-K arc minute. So if you're curious, this is not quite as deep as CMBS4 is expected to be. But it's already at roughly at half the noise that SO will get to. But it's only over about 3% of the sky. So over 3% of the sky, we are hitting these map depths right now. And we're still integrating down, so it'll get a little deeper. So this is the thing to take away from this is that these are very sensitive maps. So we looked for just some splotchiness in that CMB power, in the small scale power, where we said, how much splotchiness is there? So this is the angular power spectrum of the square of the map that's put in some proper units versus L. And you see we're down here on degree scales. And then what these points are showing you is the data. And what these violins are showing you is what we think we should be getting just from foregrounds and noise. So what does this say? It says we didn't see anything. So we're not there yet. But this is the first constraint that people have put on re-ionization. So you can say, well, so all the models that we ran gave us some expectation for this power spectrum that should be somewhere in here. And so this is the excess that's coming from just re-ionization bits. And what you see is that everything is falling inside these violins, says everything is consistent with just noise and foregrounds, but it means there's no excess power from splotchy re-ionization. So you turn that into limits on re-ionization. And so here's some midpoint versus duration. So this is work done by Srini Raghunathan, who's a CAPS fellow at NCSA. So we're not there yet. What you see is that, so here's the limit from Planck, just Planck tau. If you just say, what is the Planck tau? You say, you get some range that's like this blue line. And you see everything up here is excluded. So what this tells us is that re-ionization was not super, super splotchy. It was kind of splotchy. It might be kind of splotchy, but not splotchy enough to see. There's a little hint right here that maybe if re-ionization happened very slowly, then that is kind of ruled out by our data. So you combine that with the Planck and you see we're just starting to pinch this off. I mean, however, this is the first constraint that's not based on Planck tau, but if you then just say, well, there needs to be a Gunn-Peterson trough, like it has to be true that re-ionization was done by a redshift of 6 or so. So you put in some constraint on the Gunn-Peterson trough and you automatically have ruled out you're required to live up in this region up here. Re-ionization had to be done by a redshift of say 6 and a bit. So if you say it had to be done by 6, it had to be done here. However, what's interesting is that everything we know about Planck tau is this, like we treat Planck tau as being sort of handed down. But if we didn't know what the optical depth was to re-ionization from Planck, then all we would know is that it has to be done by 6 and that it kind of had to be ongoing at higher redshift. So with this constraint, we can say that given that it had to be done at 6, it had to happen pretty quick. It definitely couldn't have just taken its time and started at redshift of maybe 15 or 20 and slowly bubbled along. It had to actually kick in at a redshift of maybe below 5, or below 10 or so, and then get to work. So we're starting to pinch in on this, and we don't need Planck tau to do this. You say, well, who cares? Don't we believe Planck? Well, so it is a little funny. Like the CMB quadrupole, if you look at the CMB quadrupole at redshift 0, it's 10% of what it should be. So, we don't actually understand large scale quadrupoles very well. So for some reason, we've just accepted that we understand the quadrupole of CMB radiation at redshift of 6, and it's fine, even though at redshift 0, it makes no sense at all. So, however, I think the main takeaway from this is that we're starting to dig into this regime where we're starting to put limits on how re-ionization happened in a totally different way of looking at it. All right, so that's it. So here's the summary, that this is a huge signal. Like, large scale structure is a huge signal. So we can use this as a template for trying to learn all sorts of things about the universe around us. So it's interesting in its own right? We can learn FNL and use it for BAO and things like that. But this is also a big signal that we could use to try to do astrophysics with. So what could we do? Well, we could try to do things like find out where some weird things are coming from. Like, people do this with gravitational waves. We can do it with high energy neutrinos. So we can use it as a lensing source, which means we can actually do lensing reconstructions and make sure that all of our other shear measurements and things like that make sense. Or we can use it to tell us where all the electrons are, so we can learn about what the ionization history of the universe is. All right, so I'll leave it there.